Welcome for this Monday's general chemistry. We will finish chapter 1, look at some homework, and then maybe open up and start a little bit of chapter 2. But we will see how we're doing after we finish chapter 1. First things first. This is where we finished off last class. This is a generic way to approach any dimensional analysis problem here. So almost any problem in this class can be attacked taking these 5 steps. Once again, we want to start by writing down on a sheet of paper what you're given. So the value of the units. We want to, no, it's like problem solving. Let's see. Yeah, we want to essentially determine what our starting point, what we're given, and what we're looking for. So we want to read the question, figure out what numbers we have, and where do we want to go. We got to think about what relationships we can use. We're going to set up a problem, actually show it completely worked out before solving, and then checking your answer. So, hypothetically, so we're going to work a problem out. This is the step, and I'm going to show you how to do this. So hypothetically, we look at a football field. A football field is what? 100 yards? How many meters are in that 100-yard football field? So start right at, we have 100. Let's see if my other marker is any better. Yeah, a little 100 yards, and we want to go to meters. 100 yards, we're going to meters. So no matter what, we're going to start by writing down our given value, including its units. So we start with 100 yards. Now we're going to start using conversions to get this to meters. So the way I'm going to do it is not necessarily the way you're going to do it, because this is just off the top of my head. I don't know the yard to meter conversion. There's a direct one. You could use this. You could jump right there. I don't remember it. These are the ones I do remember. And you will get the same number if you do this. So I'm going to go yards to feet. So I'm going to multiply by a conversion factor that cancels out my previous unit, gives us a new unit. There is 1 yard and 3 feet. You'll notice yard on top, yard on bottom. You see that? 1 yard on top, 1 yard on bottom would cancel out. Next, I'm going to go feet to inches, because I know that one. I know that one. Feet to inches. There is what? In 1 foot, there is 12 inches. Foot on top cancels with foot on bottom. Then, now this one is the reason I chose to do it this way, because I remember this conversion. This is something that's stuck in my head. I'm crazy for it, but it's helpful for me. In 1 inch, there is exactly 2.54 centimeters. Once again, this is not something I expect you to have memorized. It's just something I have done so many times, it's there. So notice I've gone now inches to centimeters. The last step is there is 100 centimeters in 1 meter. So we'll notice centimeters and centimeters have canceled out. With all that, yards went to feet, feet went to inches, inches went to centimeters, centimeters went to meters. You could combine all these conversions together to get yards to meters. You could look that up. You say, Google, how many yards are in a meter? And you could probably jump all those steps. Sometimes you won't be blessed with all those jumps. You won't be able to just Google it up. But in this case, this shows a perfect example. So what do? Everything that is on the top of this equation gets multiplied. Everything on the bottom of this equation gets divided. So I'm literally going to take 100 times 3 times 12 times 2.54. Because that's, and you can include the times 1 if you want. You don't have to, because any number times 1 is 1. Now, that answer is 9,144. And that 9,144, I'm going to divide by 100 because I have 100 on bottom. And that means in that 100 yards, there would be 91.44 meters. So a meter is slightly bigger than a yard. So with that in mind, that's how many meters would be in a yard. That's how many meters would be in 100 yards. That answers the initial question. So you notice I started by writing down my given unit. I multiplied by a conversion factor that cancels out the given units and gets me to the desired unit. If I used multiple conversion factors, I need to plan ahead and go step by step by step. Try to cancel out the last guy and then the last guy, moving stepwise until I get to the final unit. Now, sometimes you'll have a ratio, like miles per hour. You may need a conversion to change the top and another to change the bottom. And finally, if there's an exponential given, say feet squared, you'll have to do a conversion twice. Like if I have a room that is, let's say hypothetically, let's do another problem real quick. Hypothetically, I have a room that is 50 feet squared. How would I turn this? How many inches squared would that be? And this is going to be a big number. So I've written down where I start, where I want to be. So I'm going to start with our 50 feet squared. Now, because this is going to inches squared, I have to do this conversion twice. In 1 foot, there's 12 inches. A foot cancels out 1 of the foot squared. Then I'll do that again. 1 foot, 12 inches. The second foot cancels out second foot. So I will essentially take 50 times 12 times 12, or 50 times 144. That would be 7,200 inches squared. one more just to show this in practice. Let's turn miles per hour to feet per second. Let's say if I'm going 20 miles per hour, how many feet per second would that be? So here's the big thing. I'm starting off 20 miles. Instead of over 1, it's over 1 hour. Now, how many feet are in a mile? In 1 mile, it's what, like, yeah, that's what I was thinking, 5,280 feet. So notice, that turns this to feet per hour. We've only canceled out the miles. We have not canceled out the hours. So we've now converted this into feet per hour. But we want feet per second. So in 1 hour, notice since hour's on bottom, the hour should be on top. We have 60 minutes. That turns it into feet per minute. And in 1 minute, there's 60 seconds. Minute cancels minute, leaving us with feet and seconds. So the math we would do here, 20 on top times 5,280, 280, divided by 60, divided by 60 again. So 20 miles an hour would convert to 29, technically it's 29.3, but because it's 20 miles an hour, that's the accuracy we're going to. It'd be 29 feet per second. So we're moving at a rate of 29 feet per second. Because I have all these conversions in here, the significance of my answer relies on pretty much our starting point. I'm going to assume I meant to put a period here so that we know this is 2 sig figs. That I know it's 20 miles an hour. It's not 21. It's not 25. It's exactly 20. But is it 20.2 miles an hour? I don't know. But so 2 sig figs in our starting number leads to 2 sig figs in our answer. We have a bunch of conversions that don't matter because a conversion is usually exact by definition. 60 minutes is exactly an hour. That's how we define an hour. 5,280 is maybe not exact, but that's still 4 sig figs of a conversion. So all those, so the sig figs of our starting answer result in the sig figs of our ending answer. But that's an example of what it means to be dimensional analysis. We are converting units from one to another. It's an applied math. Now, we'll start by doing simple things like this. That's more physics than chemistry. But eventually, we're going to use this to turn atoms of one substance to atoms of another substance, and we're going to use the idea of dimensional analysis to get us there. We cannot get there without the idea of we're canceling out one unit and getting another unit as a result. So, do a few more practice problems, and that should be just about the end of this chapter. So 5 mils to nanoliters. Some of these are going to be easier. And I've given you all the conversions. And this will be a trend. As we do tests, I will always give you the conversions. I may not give you the metric conversions all the time, because metric, I'm expecting you to learn them at some point. But for all difficult conversions that you may not have memorized that aren't factors of 10, I'll be giving them. I'm always trying to study application of knowledge, not memorization. I mean, there's some stuff that you do have to kind of learn and memorize, but if it's a math problem, I'm not asking you to memorize this little fact or this little fact. Just how do I approach this problem? How do I attack it? How do I think through this? So 5 milliliters, turn that into nanoliters. One of the things we haven't done in these last couple problems is think through, does this make sense? Some of these, it's not quite so easy. But so 5 milliliters to nanoliters. 5 milliliters to nanoliters. So 5 milliliters. Is a milliliter bigger or smaller than a nanoliter? Bigger. So we should expect a big number as a result. So I've given you the conversion. So in 1 milliliter, there's 10 to the negative third liters. And in 1 nanoliter, there's 10 to the negative ninth liters. So setting this up, my milliliters cancel, my liters cancel. I'm left with nanoliters as a result. So let's do that math. Now, this is a little tricky. You have to do proper order of operations, all that. But if you think about it, think about exponents and how they're supposed to work, you don't even actually need a calculator. What you should get is 5 times 10 to the positive 6th nanoliters, or essentially 5 million nanoliters. 5 million nanoliters. But try that. Try it. Make sure you get the right number. Don't just assume. Punch it in your calculator and attempt it. 10 yards to centimeters. We've kind of already done this, but we'll do this version. 10 yards to centimeters. Set it up. 10 yards. I give you, so we want yards per foot, so we want yards on bottom. Feet per inches, so we want feet on bottom. And then inches per centimeter, we want inches on bottom. So you're going to pull that up so it's a little bit bigger. Basically right here, what we've done, we've set it up so each unit will cancel out the last. So all it's a matter is reading the problem, figuring out where we go, figuring out which relationships we'll need. Keep in mind, not everything will be so straightforward where I'm going to give you all the numbers. Well, I mean, not everything's going to be so straightforward where I won't give you something extra that you may not need. Like I could say, what is the, how many centimeters are in 10 yards at 25 degrees? Unless we're physically calculating how much the metal is expanding at that temperature is not going to play any part of your answer. You'll have 25 degrees, but you won't have anywhere to put it because that temperature is not actively going to change your answer. So 10 times 3 times 12 times 2.54. 914.4. And that's pretty similar to our 91.
I'm a little confused on the answer part. Just
You would technically, how I've set this up is with that decimal here, your answer, if we were going for sig figs show, would be 910. If I didn't care, and most of the time when you're doing the math, unless I physically ask for sig figs, it's not. If you said 91.914, you would still be right. You'd still be right. So yes, sig figs are important, but on some of the rough math, I'd let it slide. And the Achieve program will also let it slide, unless it's physically asking what is the correct number of sig figs. But that is a very good point. That yes, because there's 2 sig figs in our starting unit, there should technically be only 2 sig figs in our ending unit. But the calculator will tell you 914.4 because that's what all the math gives you. Okay, and then do just one more. This one's just a silly one. 30 millimeters of mercury to torr. 2 units we are not familiar with. These are units of pressure. 30 millimeters of mercury to torr, you see? You work this out, 30 millimeters mercury. Thankfully, I give you conversions. There is 760 millimeters of mercury in 1 atmosphere. You keep going. In 1 atmosphere, there's 760 torr. So what do you notice? What do you see? You do this math. Maybe you don't even need your calculator. What happens? You have 760 on top. You have 760 on bottom. 760 cancels 760. 30 millimeters of mercury are equal to 30 torr. They're the same exact results. And as we get to the pressure chapter near the very end, we will see that, yes, millimeters of mercury were invented by a chemist named Torricelli. We were so impressed by his early barometer that we named the whole unit after him. So millimeters of mercury and torr are directly interchangeable. It's the millimeters of mercury is a direct observation. Torr is the name of the unit based on that observation. So I'm going to skip the last one for the sake of this. Last thing, this is probably the last slide. We'll be able to look at density. That's one of the things we'll be looking at in one of the first labs. We'll look at the density, the ratio to mass of mass to volume in an object. This is one of those examples of an intrinsic property that does not change. It can be used to determine the chemical identity of a substance, and we'll actually try to do that in lab. We're going to use density to figure out what is this object based on the mass to volume ratio. Is it aluminum, which has a low density, or is it lead, which has a high density? We can convert a mass to a volume and a volume to a mass using density, assuming we have the other calculation. There's 3 numbers: density, mass, and volume. If you ever have 2, you can always calculate the third. And the last thing we'll study is temperature, which is the measurement of heat flow to and from an object. The technical SI unit is Kelvin, which Kelvin can be converted from Celsius by a simple addition of 273.15. So if I am at 0 degrees Celsius, which is freezing point of water, it's 273.5. The reason why we have this conversion is because 0 Kelvin, which is negative 273.15 Celsius, is considered the lowest physical temperature that is possible, where all motion will stop. So we have this is the absolute zero. Can't go any lower than this. And so our Celsius scale is based on boiling and freezing of water. So it's not quite perfect. One last thing, we can convert Fahrenheit to Celsius and Celsius to Fahrenheit using this equation. Celsius equals 5/9 Fahrenheit minus 32. So if you have Fahrenheit, you can solve for Celsius. The harder part is if you have Celsius, can you solve for Fahrenheit? How would we do this? We have to use mathematical conversions to isolate Fahrenheit. So let's do that real quick to show you how mathematically we got to be a little bit able to think on our toes. So let's rewrite this equation and solve this for Fahrenheit. We will have to be able to do things like this in class, or at least on homework. So we have 5/9 F minus 32. Isolate the F. So first thing we got to do is remove that factor from outside the parentheses. So how do we do that? We cross multiply. We multiply both sides by 9, divide both sides by 5. What's going to happen? The 9/5 drop out. The 5/9 drop out. So we have Celsius times 9 over 5 equals Fahrenheit minus 32. So that last step now, to get Fahrenheit by itself, we have to remove the 32 from the right and put it on the left. To get it from the right, we have to add 32 to both sides. So we have now 9/5 Celsius plus 32 equals Fahrenheit. This is an example of some of the math we may have to do. If we have some number x times some factor, some number, can we solve for x? Can we isolate the x? We have to be able to do this. We will not expect you to do this right away. As I said, this is more of an Adam's first approach, but we will need to be able to do this. So be working on your math. We'll slowly get through this. But so if I have 100 degrees Celsius, 100 times 9 divided by 5, is that what? That's like 180. It's 180. If that's 100 degrees Celsius plus 32, puts it at 212 degrees Fahrenheit. So 100 degrees Celsius is 212 Fahrenheit. I do believe that's the boiling point of water. So, but that's just real quick. Heads up, we need to be able to do that at some point. We'll do this. How much volume would 13 gram sample of 2.7 grams per mil aluminum take up? So what's the volume if this is my mass and this is my density? So density is mass times mass divided by volume. How would you solve for volume? Well, you would multiply volume by both sides, divide density by both sides. So you say volume equals mass divided by density. Now, there is a way. There's a way. You can memorize these equations. But if you're using dimensional analysis, it does become readily clear. I have a 13 grams sample, grams of aluminum. The density of aluminum is 2.7 grams per mil. Now, there's several different ways I could do this. I could say 2.7 divided by 13. I could have 13 divided by 2.7. I could have 13 times 2.7. But only in this case do grams cancel grams, and I'm left with a volume up top. If I did 2.7 grams per mil divided by 13, grams cancel, but I get an answer that's 1 over mils, 1 over volume, an inverse volume, if you will. That's not what we're looking for. Only in this setup do we get a volume as our answer. Said you can learn this equation and learn how to turn this equation into this equation, but dimensional analysis should also point the way. That grams and grams cancel out. What is your unit? We are left with milliliters. So 13 divided by 2.7, you're going to get a mess of a number, but 2 sig figs divided by 2 sig figs mean the volume should be 4.8 milliliters. Same situation. 32 mils of a 0.93 grams per mil olive oil. How much would that weigh? So you can look at that original equation. Look at that original equation. Density is mass times volume. How would you get the mass? Density times volume would give you the mass. But with that in mind, you can still say what? 32 mils times 0.93 grams per mil. Mils, what are the unit we're left with? Grams. By looking at what we start with and what we want to end with, we can look at what we have to do. I start with milliliters, and I want to get to grams, so I'm going to use this density as a conversion factor to get to grams. So I know I need to multiply those together rather than divide. So 32 times 0.93 would round up to 30. So that'd be about 30 grams. It's technically 29.76, but with sig figs and all, it rounds up to 30. Then finally, last one. At what temperature Fahrenheit would 150 Kelvin occur? So this one is a tricky one. You have to do 2 conversions. I have to turn Kelvin to Celsius and Celsius to Fahrenheit. So Kelvin to Celsius, not as bad. Kelvin minus 273.15, which most of the time we're going to just say approximately 273 equals Celsius. So 150 minus 273 equals, you can do that. Now it'll give us Celsius, our first starting point. So we don't have a direct leaping point from Kelvin to Fahrenheit. So negative 123 degrees C. Now the equation we just gave earlier, 9/5 Celsius plus 32 equals Fahrenheit. So 9 over 5 times negative 123 plus a positive 32. So negative 123 times 9 divided by 5 is negative 221. We're going to add 32 onto that to have this be negative 189. So that's negative 189. That's where 150 Celsius is at in Fahrenheit. Yes, I realize. Oy, that's a little bit of tricky math, but that's where we're ending the chapter. So I want to try to push us a little bit. But that's the end. Wanted to look at a few homework problems. We got like 10 minutes left. With 12 really, but so these aren't due for a while, but I wanted to use this as practice. Remember, the reading assignments and the learning curves I do believe are due on Saturday. So if you had trouble getting access, come see me. I will be glad to try to help you. If you are stuck at home for whatever reason, and we'll Skype you in. I'll try to Zoom meeting. I can take control of your screen. I can try to help you as best I can. So don't feel like, as long as you have internet access, I should be able to help you. So I'm going to skip past the easy ones and move straight to dimensional analysis and sig figs. Because, I mean, so your numbers may be slightly different from mine. So don't worry about that. I'm trying to, your problems should be more or less similar. Oh, come on. Okay, there it is. Let this be like a how-to, not a here is the answer. Let's look, is this one? What's this one? Okay. We'll do this one. This one is catching on my cord. Number 16. Convert the given lengths to the indicated derived unit. 1.59 kilometers, 1.59 meters to kilometers. 0.00484 meters to nanometers. 17.9 centimeters to, meters to centimeters. This one is actually rather easy. Though just in case, we got a hint here. What does the hint tell us? Oh, it tells us mega, kilo, deci, centi, milli, micro, nano. So it gives us all the conversions lengths. This is how many of this unit is in 1 meter. How many of this unit is in 1 meter? So we can go from there. Since all of these, we're going to meters, from meters. So 1.59 meters. There is 1,000 meters, 1 kilometer. So literally, it doesn't even say, put this in like scientific notation. So all we have to do is say 0.00159 kilometers. Just make sure you have the correct number of zeros. We have 0.00484. 0.0484 meters. We're going to nanometers. We said in 1 meter, well, there's 10 to the negative 9th meters in 1 nanometer. There's a whole heck of a lot of nanometers in 1 meter. So there's a very, very, very small conversion. In case you goof this up, think about this. We're turning a big number into a small number, so we should have a lot of small units. This should be a very big lot. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We should have 4,840,000 nanometers. If you do this math and you get a really small number, you hopefully will think nanometers this, meters this. The size differences should give us a lot of nanometers. Last one, it's 17.9 meters in a centimeter. 17.9 meters. And there's 10 to the negative second meters in 1 centimeter. So basically 1790. Once again, centimeters smaller, we should expect a larger amount. That's just a number. That's just a thing I picked up at random. I'm going to move on. Let's see. Find an actual hard one. That was just one that, well, I stuck with it because I'm stubborn. Okay, this one's a little bit easier. I'm moving at 77.7 centimeters per second. What is my speed in kilometers per hour? Once again, I think they give you, here's a list of common metric prefixes that are helpful. You need to know how many seconds are in 1 minute and how many minutes in 1 hour. That's all you need from there. They don't straight up and give you the conversions, but there is a link that will take you straight to the conversions. Now, as you do this one is number, someone can probably read it better than I can, but my eyesight's, I have to read a board from sideways or tiny little screen. So you may not have 77.7. You may have 66.3. It doesn't matter. The same general process holds true. So even if you can't copy the number word for word, you can still learn how to do this. 7.7 centimeters, 1 second. I would say, oh, there is 100 centimeters, 1 meter. 1,000 meters, 1 kilometer. I'm going to run out of room so people won't be able to see too well. Ooh. Let's see. Then, since seconds are on the bottom, we're going to say 60 seconds, 1 minute, 60 minutes, 1 hour. So this differs from the last one we did in that we changed from, say, miles per hour to feet per second. Now we're changing from centimeters per second to kilometers per hour. We're essentially going backwards. But what are we doing? We're canceling 1 unit, the next unit. We get to the final unit, kilometers. Then we go back, we cancel seconds, then we cancel minutes, and we're left with the last unit, hours. So working that through, my number should read, so divided by 100, divided by 1,000, times 60, times 60. My number, because this is 3 sig figs in my starting number, I will have 3 sig figs in my ending number, 2.80. My calculator wants to say 2.7972. But 3 sig figs in my starting number, I should probably have 3 sig figs in my ending number, 2.80 kilometers an hour. So that's just a quick example of dimensional analysis in practice. So right now, this isn't really, okay, I'm going to skip around. Want to do one sig fig problem. Now that's a Celsius, that's a temperature conversion. I'm jumping up. Some of these, like this one, some of these might be like setting up, or it's already set up and you have to just do the math. Make sure you do the, okay. Okay, this one was what, number 12, I think. We'll just finish with this problem. We'll probably run out of time. But it says 101 centimeters minus 99.1 centimeters is 1.9 centimeters unrounded. According to after rounding, the answer should be reported to which digit and thus has how many sig figs. All this comes down to is setting these up. 101 minus 91.1. Oh, sorry, was it 99.1? Setting that up. We would like to keep it at 1.9, but we are not blessed with that. Setting that up, 101 ends at the 1. We don't know what the decimal is at 101. Because that is unknown, we keep only the location. Setting that up, even though it says 1.9 is the result, we have to round that to 2. So we round to the ones place, meaning we only have 1 sig fig after all said and done because of that. I know that sucks, but that's how it is. Because we don't know what that is, we can't state what that number is definitively. But we do know whatever it was, it should round to 2. Should round to 2. The next one, 0.5 plus 9.8. Let's see. Yeah. 0.5, 9.8. You add that 10.3 unrounded. Well, blessed be. All the numbers come before the line. So that means all the numbers are significant. This is a question mark, but so is this, so we don't even bother. So this would be rounded at the tenths place, and it would have 3 significant digits or 3 significant figures. So when you add and subtract, we keep the location of the furthest left, the location of the sig figs. It's hard to say. It's like, which one has the least sig figs from the right? We keep the lesser of the 2. So both of them have a sig fig at the tenths place. So neither of them loses. And the previous guy, one had a sig fig at the ones place, one had a sig fig at the tenths place. And so we lost at the tenths place. Now when we do a multiplication or division, remember we keep the number of sig figs, not the places of the sig figs, because we can vary so wildly. But okay, that is where we're going to stop for today. We have finished chapter 1. We will start Wednesday with chapter 2, where we start looking at the atoms and how to name them. This is Andrew Evans signing off. Have a good day.